Thank you. It's a delight to be here and speak about Philip's work. The traditional role of a discussant, invited discussant, is to provide a little perspective on the speaker's work or on the topic about which he spoke. The traditional method for doing this is to begin by saying, this is wonderful work and it reminds me of my own wonderful work, and I'd like to compress an hour talk into 10 minutes to discuss that. So Finetti argued, and Philip helped to illustrate, that objective probability does not exist. Rather, that probability is only a tool for describing and quantifying and manipulating our personal ignorance and uncertainty about future events. I'd like to present the startling, conflicting view that sometimes it kind of does. And I'm going to take ideas from the first Finetti speaker, Percy Diaconis, an amazing lecture that he gave that I heard 30 years ago and has affected me a lot. Percy and a student of his, Eduardo Engel, considered the problem of throwing a dart at a checkerboard pattern target. Actually, they had striped target, but I like drawing checkerboards better, so I'm going to convert it just a little. Is the event hit a dark square random? Well, does it have a well-defined objective probability? Does the concept of objective probability apply? So here's a wall divided up into just two squares, and even a mediocre dart thrower can influence whether or not the dark rectangle is hit. So if we have someone drawn from the audience, we give a dart to this person and ask them to throw at the wall, then the concept, the event, dart hits dark square, does not have an objective probability. We can't have a probability that we all agree on. It depends on the intentions and the skill of the dart thrower and how much we know about those. Well, what if we look at a 2x2 square? Now it's a little harder for the dart thrower to pick exactly where he or she is going to hit. It gets harder and harder as we take more and more grid cells. And finally, when we get to a very refined grid, it becomes essentially impossible for us to predict exactly what is going to happen. And no matter what probability distribution the dart throwers' darts have on the wall, the probability of hitting a blue square is going to be very close to 1/2. The randomness isn't a binary property. It isn't that something is or is not random. There are degrees. With a tiny n, the event dart hits the blue doesn't have an objective probability. With a huge n, you notice the n is much larger now. The event dart hits the blue does have an objective probability of about 1/2. You can be quantitative and, if your probability, subjective probability, is something other than 1/2, then you can be attacked by a Dutch book argument. I'm imagining that would happen by a Dutch bookie or a boekmaker. So you're pretty much forced to have a probability, subjective or not, of about 1/2 for blue squares. So for small n, all bets are off. Only subjective probabilities are applicable. But for huge n and other problems like this, that say genetics, in cosmology, any time that there are huge numbers of very similar events occurring, we begin to have the possibility of, in the limit, an objective probability with, and if you fail to follow that, to assess properly that objective probability, then you'll be subjected to the losses for a Dutch book argument. You can show in the dart throwing example that if we have an n by n rectangular square, then a grid, then the probability of dark square is close to 1/2, that its upper bound is some constant c that depends on how smooth the dart throwing distribution is divided by n. So this is disappointing, of course. So Bruno, Finetti, and Philip are both pushing us toward the practice of soliciting subjective probability distributions and for assessing scientific uncertainties. But in the problems that we face as scientists in the 21st century, this just isn't practical. There are, in the toy problems that we use in presenting philosophical arguments like this, it may be possible to assess probabilities subjectively, but in most of the scientific problems that we face, we have huge numbers of uncertain quantities about which we just don't have the time, energy, or insight to make meaningful assessments. And so we're thrown with little other choice than to use the so-called objective Bayes or at least diffuse priors in higher levels of the hierarchy. We have often so much data. The new telescopes and satellites are giving us terabytes a day of data. For the genetic data comes in similar amounts. We have so much data that we begin to be able to map the tails of distributions in quite some detail and find that conventional parametric families all fail. And so we may be forced to look at non-parametric Bayesian methods. And in both of these cases, the idea of using subjective probability and being careful about and thoughtful about picking our prior distributions is an unattainable goal. There seems to be an emerging consensus that what we should do is to use automatic procedures like reference priors or such for most of the assessments that we're forced to do, and to be subjective and thoughtful about the few that actually matter. So that's all I have for today. I just want to thank Chris for inviting me, Bruno de Finetti for giving us something to talk about, Percy Diaconis for just brilliant insight in many points, and a polite audience. That's you, thanks. And Phil David for a delightful talk.